Hello and welcome back to Unit 3. This is the last part of Unit 3, and in it we are going to work two more two-dimensional projectile motion problems. The first one involves a ball being launched from the ground at a speed of 30 meters per second at an angle of 60 degrees to the vertical. You want to know how far away does the projectile land from its initial launch point, and how high does it go? So in a great many ways, this particular problem has two parts to it because you're looking at two different final locations for the two parts. Okay. Begin by drawing our picture. We are told a ball is launched from the ground at an initial velocity of 30 meters per second with respect to the vertical. So our 60-degree angle is here. I'm going to let the ground be 0 meters and the launch point be 0 meters. This projectile is going to go up and come back down. This is going to be y for part B. So I'm going to just do it like that, I guess. And this will be y for part A. So how high does it go? It's the maximum height. And how far does it land from its launch point? That would be back down at the ground. Okay. I can see already that our initial velocity is going to need put into components. In this case, our triangle looks like this. Here is theta, here is V naught. This side is V naught, V naught x. And that is going to be V naught sine theta because it's on the side opposite. This side will be V naught y, and it will be V naught cosine theta. I can now write my grocery lists. Okay. And then start plugging in. Right. I forgot the acceleration due to gravity on the picture, so I added it. Our initial position is 0 in x and 0 in y. Our final height, y equals 0 meters, and I'm going to make a little note here that this is for part B. For part A, it's a question mark. Our final velocity in y is going to be 0 at the top, so I can put that in. Or, if we go back to the ground, it's going to be the negative V naught y. Well, if I plug in V naught is 30 meters per second and the angle of 60 degrees, that gives me V naught y is 15 meters per second. And I've got to watch out because Vy is going to be downward, so I've got to add a negative sign given my up is positive coordinate system. Vertically, the acceleration is 9.8 meters per second squared downward, which in this coordinate system makes it negative. A sub x, the horizontal acceleration, is 0. The horizontal velocity, V naught sine theta, if I plug those numbers in, I get 26 meters per second. And that allows me to fill in Vx as well because, again, acceleration is 0 that way. And this x is what I want to find for part A. I actually miswrote this over here. Oh, no, I didn't. I just have my labels backwards. So let's go back to y and make sure we get this correct. For part A, we're going up and returning to the ground. How far does it land from its initial launch point? That tells me my final position is 0 for part A. And how high does it go is the question mark for part B. Okay. Let's consider part A first. Part A wants to know position X. We know that to find position X, we have to know T. In order to find T, the easiest way is to use this equation in Y. Because we can invoke symmetry in this case, we know Vy is negative 15 meters per second. V naught y was a positive 15 meters per second. Acceleration is 9.8 meters per second squared downward, which brings in a negative sign. And solving all of that for t gives me 3.06 seconds. I'm going to make a little note here. This is to the original height. Okay, now that I know t, I can come over and find the horizontal distance. Initial distance was 0. Initial velocity in the x direction was 26 meters per second, and I'm going to multiply that by 3.06 seconds. And that gives me a horizontal distance of 79.6 meters. For part B, I'm going to again invoke symmetry. By symmetry, I know that time up equals time down because I'm starting and stopping at the same height in that case. This problem is focused on, or this part of this problem is focused on going to the top. Well, because time up equals time down, that means that time up will be 1/2 the total time, which is 3.06 seconds. Or, in other words, 1.53 seconds. Knowing the time, I can jump to this equation. Y naught was 0. V naught y was 15 meters per second. A time of 1.53 seconds. 1/2 of negative 9.8 meters per second squared times 1.53 seconds. And multiplying that all out gives that the maximum height is 11.48 meters. Okay, last example for this part and this unit deals with a fire hose. This fire hose is being held near the ground and it shoots water at a speed of 6.8 meters per second. And we're asked what angles should the nozzle point in order that the water lands 2 meters away. The other thing you'll notice on this slide is that lovely link. I'm going to encourage you, if you like, to follow it. What it is a list of trig identities. And I want to remind you of one of them because we're going to need it later in this problem. The double angle formula for sine. Sine 2 theta is 2 sine theta cosine theta. Okay. We are given some information in this problem. We are told how far away the water lands and at what speed it is launched. And what we really want to know is angles. And because we really want to know angles, that makes plugging in numbers in this particular problem a little bit cumbersome at first. So I'm going to work the problem symbolically to begin with. Okay. So drawing a picture. Don't forget gravity this time. There it is. I have my water going up, coming down to the same height. it is launched at V naught, and I know that V naught is 6.8 meters per second. Here's the angle I want to know. I'm going to let the launch point be 0 in both dimensions, and I'm going to let the maximum distance that the particle goes be r for range. Okay. I can draw my favorite triangle. I have V naught on the hypotenuse. V naught y will be V naught sine theta, because it's going to be on the side opposite. I should put my theta in there. And V naught x will equal V naught cosine theta. With all of this, I can now write the grocery list. And since I'm here, I just want to make a quick list of the things that I know so I can plug them in easier later. I know the range in this case is 2 meters, and the initial velocity is 6.8 meters per second. I will plug them in, I'm just not doing it yet. Okay, vertically it starts and stops on the ground, so 0 it is. I can again invoke symmetry. Since I'm starting and stopping at the same height, my final velocity will be the same as my initial velocity, but in the opposite direction. So there's a negative sign. Okay. And my acceleration is negative g. So I've already taken into consideration the directionality, and g is just a number. It's a magnitude, if you will, and it has a value of 9.8 meters per second squared, so I can add that to my list of known quantities. Okay, well, I need to find angle, and angle's not something that I'm really familiar with finding usually. Usually that's a number that's given. So instead, in order to kind of figure out a way through this, think about the information you're provided. You're provided with a range. You know how far this water goes before it hits the ground. So it seems logical that you would have to use the x equals x naught equation in order to bring in the piece of information you're given. But as we've seen, in order to use that equation, we have to know time. So it makes sense that you're probably going to have to find time first. If you look at the vertical equation, you have all the pieces there to use the y equals y naught equation to find time. So let's start there. Okay. V naught y was V naught sine theta times t plus 1/2, watch out for that negative gt squared. Solving for time, there are two possible solutions. One is that time equals 0, not a big surprise. The other one is time equals 2 V naught sine theta divided by the acceleration due to gravity. This equation will give you the time of flight for whenever you're starting and stopping at the same height, assuming that everything is set up as shown in the diagram here. Okay, just really quick, if we think back to the last question, we also started and stopped at the same height. However, our range equation would not work for the problem as it is drawn, because the angle is defined with respect to the vertical instead of the horizontal. So you'd have to do a little bit of work before you could just use this equation. Now that I know time, I can bring in the range that I'm given. So r equals 0 meters plus v naught x is v naught cosine theta times time, which is 2 v naught sine theta divided by g. Okay. So getting rid of the parentheses, if I look, I have a factor of 2. So I'm going to put that there, and I'm going to write things a little bit funny and sort them as I go. It's all multiplied, so I'm able to do this, or multiplied and divided. I have a v naught here and a v naught there, so I'm going to stick that over here. I have cosine theta, and I have sine theta. And the last piece I have is g. And now if you look, sitting right there in those beautiful parentheses is the body of that trig identity that I gave you at the beginning of this problem. So I'm going to take and invoke that trig identity and say that my range is going to be v naught squared divided by g times the sine of twice the angle. This is known as the range equation. Okay. So r equals v naught squared sine 2 theta divided by g. I can now rearrange that so that I can pull the angle out of the sine. Okay. And at this point I can also plug in numbers. My range was 2 meters in this problem. G is 9.8 meters per second squared. And V naught was 6.8 meters per second, the whole thing squared. And if you work that all out, you get sine theta equals 0.42. Taking an inverse sine gives you that 2 theta equals 25.07 degrees, which means theta equals 12.54 degrees. Okay, but remember when we first started looking at 2D projectile motion and the fact that there were two angles symmetric around 45 degrees that would hit the same range. Okay. To see where the second angle comes from, we need to consider the graph of, in this case I'm going to do phi, sine phi as a function of phi. Okay, our sine goes up, comes down, comes up again. Okay. And if we look in the first and second quadrants, there are two places where sine phi crosses a particular, or two angles where sine phi equals the same number. And those two angles are going to be symmetric around 90 degrees. Okay? Which means if this one is 25.07, that means that that one is 154.93 degrees, symmetric around 90 degrees. So I'm going to put an or up here. 2 theta equals 154.93 degrees. And now I can take that angle and divide by 2 and find my second angle of 77.47 degrees. And if you look at them, the two angles, 12.54 degrees or 77.47 degrees, are indeed symmetric about 45 degrees, as given or as shown in the simulation we looked at the start of our analysis of 2D projectile motion. This concludes this part. It also concludes this unit.